Bismillahirrahmanirrahim. Assalamu alaikum. So let me recall slightly generalized version of Ito formula. So it says that if I have a function which is theta and it is depending on time and a Brownian motion, that its differential d theta is given by partial derivative of theta with respect to Brownian, partial derivative of theta with respect to Brownian, d Brownian, and plus partial derivative of theta with respect to t and plus 1/2 second partial derivative of theta with respect to Brownian dt. So that's how the slightly generalized version of Ito lemma look like. So when my theta is depending on time and the Brownian w of sub t, right? So now I will use this towards we will be basically driving the first integration by parts formula, and we will take the help from here. Now let's define a particular function theta. So let me set theta to be equal to the product of a function f of t, this is deterministic function, times g of w sub t. So this g is depending on Brownian and f is depending on time. So I need to compute the d theta. So I am interested in finding out what is my d theta. So what I need to compute the partial derivative of theta with respect to w, theta with respect to time, and second partial derivative of theta with respect to w. So the first partial derivative of theta with respect to w is going to be nothing but f of t times the derivative of g, right? And of course the second partial derivative of theta with respect to Brownian is going to look like f of t times second derivative of g, right? And we also need to compute the partial derivative of theta with respect to t, which should be the derivative of f of t times g of w sub t. So now I will substitute all of these values into the formula. So first I will put the value of partial derivative of theta with respect to Brownian, which is nothing but f of t times the derivative of g of t and dw sub t, plus so time derivative of theta, which is f derivative times g of w, and plus 1/2 times f of t multiplied by second derivative of g dt. Or we can write even in more better form. So d theta, so like theta is equal to f of t times g of w sub t. It should be equal to f of t times derivative of g of t, g of w sub t, dw sub t, plus f derivative with respect to t, g of w sub t dt, plus 1/2 f of t times second derivative of g with respect to w and dt, right? So that's how the Ito lemma or the differential of this product will be given. Rearrange this and isolate this term on one side. So this implies that f of t times g prime of w sub t dw sub t is equal to differential of f of t times g of w sub t minus f prime of t gw sub t dt minus 1/2 times f of t second derivative of g dt, right? And let's now integrate on both sides from a to b. So when we integrate this from a to b, So integral from a to b on both sides, a to b, integral from a to b, integral from a to b. So I can simplify this to get this left side will remain the same, but on the right side this term is going to be f, only the product of f and g, because d differential and the integral will cancel out each other, but these two terms will remain as it is. So I like we can pull this one up, 1 upon 2 outside only. So with this, my first integration by parts formula is going to look like integral from a to b of f of t times g prime of w sub t, t w sub t to be equal to f of t times g of w sub t from a to b limits minus integral from a to b of f prime of t g w sub t dt minus 1/2 times the integral from a to b of f of t times the second derivative of g with respect to Brownian dt. So this formula is known as the first integration by parts formula. So this is known as first integration by parts, integration by parts formula for stochastic integrals, right? Let's apply this formula onto specific cases. Number one, let me set g of w sub t to be equal to only w sub t, like g is given by just the Brownian. So in that case, my integral from, so its derivative g prime with respect to w is given by 1, and its second derivative is of course going to vanish, so it's 0. So this term will be 0 in this case, and I will be left with integral from a to b of f of t times, so it's 1, so dw sub t equal to so it's f of t times f of t times w sub t a to b minus a to b integral and f prime at t times, so g of w is basically w sub t dt, right? So that's a kind of one consequence out of this first integration by parts formula. On this side, this left is a Wiener integral because it is deterministic function and we are integrating it with respect to some randomness, which is Brownian. The second consequence, or the second result out of this, which we can obtain, let's take f of t by setting f of t to be 1. So like if we take f of t to be 1, then what we need, first derivative of f, which is going to be 0. So now we can use this data over here, and what we will be left with is integral from a to b. So f of t is 1, so we will only left with the derivative of g dw sub t to be equal to f of t is 1, so it's like g of w sub t from limits t to be a to t to be b minus times minus integral from a to b. So now my first derivative has already vanished, so this term is going to be 0. So this term is going to survive 1 over 2. So it's the second derivative of g, because f of t is already 1. So second derivative of w g and dt. So that's the second consequence, or the second result out of this, first integration by parts formula. So the last result that we have recently obtained is integral from a to b, the first derivative of g dw sub t to be equal to g of w sub t from a to b limits minus 1/2 times the integral a to b second derivative of g dt. Now if we set g of t to be a function w square by 2, g of w sub t to be w square by 2, then its second derivative, first we need its first derivative, so its first derivative is w sub t and its second derivative is of course going to be equal to 1. So in this way we can write from a to b. So I will put the value of this first derivative, which is w sub t dw sub t, to be equal to g of w sub t, which is w sub t square by 2 integral from a to, or limits from a to b, 1/2 times a to b, the integral of 1 dt. And then you just need to put these limits, w sub b square minus w sub a square divided by 2 minus 1/2 times this integral is b minus a, because it is from calculus 1. So that's the stochastic integral of w with respect to Brownian. So Brownian with respect to Brownian can be given by this. Much more to come. If we set a to be 0 and b to be capital T, then this integral from 0 to t of the Brownian is given by Brownian square at capital T divided by 2 minus 1/2 times capital T. That's how we will compute more in the coming videos.